Ready or not, here we are. There's Ponca. Let's see, there's Alva. So let me see if I can actually make a camera work here in Alva. Hey, there we go. Yep. Somebody speaking Spanish in the store. I heard "Cómo estás?" Hey, are you going to fix that camera view for me?
Yeah, I am. Yeah.
Okay, thank you. Sweet. There we go. Nice. Thank you.
Yep.
Man, where is everybody? Is everybody boycotting me? Did I make everybody mad on Monday? Well, it's supposed to start with this recording popped on, so that pretty much tells us it's 3:25. Hey, Jessica. How are you, Brittany?
I'm all right.
Good. All right, so we'll go through reading it here. I've got Christina, I've got Brittany, I've got Whitney, I've got Josh, I've got Jessica. Cool. And let's see, I've got Mario out in Woodward. And let's see, Ponca, I think I saw Adam and Justin.
Yes, sir. And one other one now.
And Derek.
Yep.
Okay, cool. Don't see Rachel yet. All right. And Alva, let's see. I see Liz.
Yep.
Yep. All right. And who else do I have out there?
Jessica.
Cool. All right. Anybody else?
Erica.
Erica's there. All right. Who else?
Kelsey.
Chelsea? Chelsea's
Kelsey.
there. Sweet. Cool. And I have Kelsey or Chelsea? I'm sorry.
Kelsey with a K.
Kelsey's there. All right. Sweet. All right, well, I'm going to go ahead and jump in to where we were. So I think me talking about how this ball of cells on top of your shoulders is pretty cool. Pretty complex. That we had, how many billion neurons again sitting up here?
5 trillion, 500 trillion or something.
100 billion with how many connections total? 500 trillion. Yeah, good memory. There we go. All right, so you used some of those connections that I formed a new connection. So we're going to go into, I'm going to vary up my presentation. It's just not going to be all me talking. So I'll add some multimedia stuff in there, some YouTube clips to help break down what I'm talking about. So we really want to get an idea of brain functioning so that we understand what we're trying to do when we're working with folks that have addictions. Because like I've said before, we'll have a pretty clear roadmap of what we want to do, but we want to know why. So then you're like, well, why is this hard? If you have this clear roadmap and you have all these techniques, then why is this hard? So I'm going to show you why it's hard and why addiction costs people so much of their lives, of their finances, of their families. So we should hopefully understand a little bit more of that by the end of today. That is my goal. So to do that, we really have to understand kind of on a really basic level. And I'm not going to try to go into, I mean, you'll see some pretty detailed illustrations today, but I don't want to get into too much of neurobiology. I think having a working knowledge fits the definition of what we're working for in this class, which is to be able to do counseling with substance use. But we do need to try to understand how neurons work. So I've got a picture here on the PowerPoint illustrating what a couple of neurons look like? You know, a couple of brain cells. And so you see all these wires and all these little places where they connect. So we're gonna talk about that a little bit. So you see a picture of a guy here, and he's got some things in his hand. What's this dude about to do?
Shock somebody.
Yeah, he's gonna shock somebody. Why is he gonna shock somebody?
Bring them back to life.
Get their heart going again. Absolutely, yeah. If you see this guy like this is bad news for you, because your heart stopped, and they're trying to get it started. They're trying to get it started again. So I never really want to see that ever. I'm in a bad way. Well, you know what we could do is if we had the time, if we weren't in an emergency situation where we need to keep blood flowing through your body, we could go into your medulla oblongata, which we talked about yesterday or Monday, and we could hook a couple of electrodes up there and send an electrical impulse to get your heart beating again. Anybody know anybody with a pacemaker? What's the purpose of that pacemaker?
To keep it steady.
To keep it
constantly.
I don't know the medical term.
No, that's right. You want a sinus rhythm. You want a static rhythm. You want a steady heartbeat. My dad had one. He had a regular heartbeat towards the end of his life, and so it would pause. And you don't want that pause. You want it to be like a quartz time clock. You want it to be right on rhythm. So that rhythm runs on electricity. So we're right now. You all are sitting here, and there is electricity flowing to your heart, telling it to beat. Hopefully somewhere between 60 and 80 beats per minute. So if any of us got underneath, and we've had a lot of electrical storms in Oklahoma, it's kind of nice in August to actually have rain around here. It's kind of not the norm for those of you that are from Oklahoma or not from Oklahoma. What happens if you get struck by this lightning bolt right here?
Chances are you won't live.
There's a good chance you're not going to make it because you've got electricity already going on. You don't need any more. So if I already take a fork and there's an electrical outlet down here and stick that fork, I'm not going to be the same after I do that. It's gonna hit me pretty hard. Hopefully I don't go into cardiac arrest. I'm definitely overloading my systems. We're running on electricity right now, which is interesting to think about. We don't think about that. We are also running on chemicals. So this is where substances come in. Drugs of abuse. So what we're looking at, our brains are working on an electrochemical process. That's neurotransmission. So I'm going to pan out a little bit here so people can see. So you guys are taking in information about me, able to see me moving around. It's early in the class. Normally when I do this, it's in a 3-hour class, and people are really bogged down and tired by this. But everybody's fresh coming in at 3:30. Anyway, so you guys are taking in information about me, and your eyes are translating that information into an electrical impulse. So it's going to hit the back of your eyeballs, your retina, and it's the information's translated into an electrical current, and it passes through the optic chiasm right in the middle of your brain, and you get back here in your occipital lobe, you get an impulse that hits there, and it sends on information. Basically, what's happening is you have visual cells, and so this would be a neuron related to vision, and it has a nucleus, and so it's getting information, and it's basically a relay station. So it sends it to one neuron, which sends it to another. This would represent another neuron, kind of like this illustration here. So let's just say we had a bunch of neurons. So it'd be boom, 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 and it's happening just at the speed of light. It's happening very, very quickly. So let's say that the electricity hits the end of your neuron, where those connections are. actually, all of those little connections are not connected. There's actually a little gap. There's a little space called a synapse. So actually, if all of our neurons were connected, we'd never be able to do anything because we'd be overstimulated. We'd just be in a constant state of too much. Because when our, for instance, what I'd like for you to do is I'd like for you to close your eyes with me for like 5 seconds. So everybody go 1, 2, 3, 4, 5. Okay, open them up. Okay, so while your eyes were closed, what happened to that electrical signal? It went away. And the way that it went away is that there were chemicals being released down here when the electrical signal, when your eyes are open, boom, it hits the little gap there, the little synapse, and there's little chemicals that are released. And they go from the top neuron down to the bottom neuron. The sending, the one that sends the information is called the axon. The one that receives the little chemicals, that's called a dendrite. So you have an axon which sends, and you have a dendrite which receives. And so this would be a neurotransmitter right here. This little blue dot represents, let me circle it for those off campus. That's a neurotransmitter right there. And that's basically a fancy word for brain chemical. So again, we're running on electricity, we're running on chemicals. That's basically it. In a nutshell, that's how we're walking around. We're a product of this electricity counter interacting with chemicals and a chain reaction, and that's who we are. That's how we operate. And these cells are either on. It's a binary logic. They're either firing or they're not. Oh shoot! Which mine are not firing because I just completely got out of my PowerPoint. From current slide. Okay. On, off. On, off. Sorry, okay, I'll stop. Okay, so the main thing to think about is when your little when this went away, when you shut your eyes, what happened was you have a little thing. You have little things like vacuums. It's a process called reuptake. And what made the image of me go away was that these little vacuum cleaners in your brain, well, not really, but they act like vacuum cleaners, turned on, and they sucked the chemicals back up into the sending neuron. That's a process called reuptake. So your chemicals are supposed to, in theory, your brain chemicals, go and attach, and then when they're done, they go back and they recycle. Like that. And so the chemical most responsible for your vision is a chemical called serotonin. And so right now we have a neurotransmitter called serotonin that is helping us see. That's going to be important. When I was in school, we knew of about 55 different neurotransmitters. We don't know of that many more. We have a limited number of chemicals in our brain. And we'll talk about why that's important in just a few minutes.
Sorry, what did you say serotonin helps us?
Serotonin, well, I've got a slide to help. Don't worry about the notes yet. I appreciate that. But yes, it helps us with vision. It's involved in our senses. What else is serotonin famous for helping us with?
Mood balance.
Feelings. What did you say?
Mood balance.
Mood balance, yes. Feelings, mood. Serotonin is very influential in our mood as well. So it does more than one thing in our brain. Okay. The main things to get here are electrochemical. Electricity causes a release of chemicals. Our body recycles those chemicals through a process called reuptake. And there I've got it right there on the slide. So circle that because that'll probably be on exam somewhere. Okay, our brain cells are also limited. We have what's called a refractory period. Okay, so all neurons just can't just stay on constantly. They fire. They're like electrical impulses. You know, think about your heart, for instance. You know, I think that's a pretty good example because we can, you know, picture and imagine and put our hand on our chest and feel our heart, you know, pumping like that. The electrical waves and chemical processes going on in our brains are much like that. I mean, they're not like the lights in this room where you just flip the switch and they stay on. And you're like, well, Taylor, you know, our vision, I can see. Well, yeah, but it's happening very quickly. You know, your visual neurons are firing all the time. And we process that serotonin a lot. But what happens is we have this thing called an action potential. That's the actual wave that releases it releases the chemical into the synapse. And then your cell rests for a minute, and that's called a refractory period. And then it could either fire again, or it could not. And so if you shut your eyes, obviously your visual neurons aren't going to fire. So I ask you, and this is for your talk to me about psychopharmacology. This is more than psychopharm, getting into neurology this way. What does this have in common with the male orgasm? Sometimes you just have to wait a little bit for that neuron to fire again. So anyway, I'm sorry, that's a bad reference and it's kind of out of context, but keep people awake. You know, it's just like it's 3:40 on a Wednesday. So your brain cells have something in common with male orgasm. Right. So I want you to see kind of the action potentials the brain cell is firing. We'll show you a couple of videos to help illustrate that. Hopefully. Oh, I've got two of them coming.
Done me and you bet I felt it. I tried to beat you, but you so.
I don't think this was it. Hold on, just one moment.
I was enjoying.
I was just having a very beautiful.
It was chilled. It was not bad. Let's see here. Was this it? Oh man, that's not the same. Okay, I want you guys to see something here. This is not the same.
I really like that song.
Can you copy and paste? Maybe it's.
Maybe you're right. Okay, thanks, Josh. I'll try to copy and paste it. Okay, because this is not the same address. You notice there's different characters here. Hold on.
We had to exit.
Man, I even tried this right before I came to class to make sure that worked. Let's try that one. There, okay.
A neurocell or neuron.
It's much less cheery.
This neuron is shown 20,000 times larger as in reality. At this tremendous magnification, a hair would be 6 feet thick. These incredible organic chips function through electric signals. They control nearly everything we do, from thinking to moving muscles, from sensing to hearing, and even watching this video.
Okay, so this is the axon.
Thin extensions at the top of the neuron are called dendrites. These dendrites receive signals from other neurons. As long as the inhibiting blue signals dominate, a neuron will remain silent. But as soon as the activating red signals dominate, an electric pulse is sent through the thick lower tube of the neuron. This tube is called the axon of the neuron. Neurons are not alone. The brains of a human contain 100 billion neurons. If we were to walk through a single human brain at this pace, it would take over 300 years to just take a glimpse of all the neurons. We are now zooming in up to a magnification of 20 million times. At this scale, a hair would be over a mile thick. Each neuron contains billions and billions of proteins. These proteins are tiny little machines, each designed to do a specific job.
Okay, so what are your thoughts on the neuronal illustration?
Some intense zoom.
There was some intense zoom, a mile thick hair strand. Yeah, that's pretty crazy. What else? Kind of talked about taking 300 years to walk through, the brain and see all the neurons. So, it's massively complex. Hopefully, it kind of gets you in the mindset of what's going on. All right, let's watch the exciting one now.
Willie, you done me and you bet I felt it. I tried to beat you, but you're so hot that I melted. I fell right through the cracks, and now I'm trying to get back. Before the cool done run out, I'll be giving it my
Okay, so what you're actually looking at here, we didn't go into, these are myelin sheaths, and that actually makes the action potential of the electricity go faster. So the more that you use a particular part of your brain, let's say you're trying to memorize something for substance abuse counseling. Let's say that you're trying to memorize that the brain has 100 billion cells. So when you thought about that, when you experience that, when you get a reinforcement, there's little proteins that bind, and these are called glial cells, and they cause it to be more. They cause it to transmit more efficiently. The electricity just flies down. It like I can't remember the exact rate, but it increases the rate exponentially because it just boom. It's easily accessible, and so you have a bunch of neurons in your hippocampus that have to do with memory. And so when you're learning new things in school and you're learning new things in college, your hippocampus is forming massive networks, especially when you're studying for an exam and trying to cram and reviewing information and repeating and repeating and repeating. So you have it, so you have that information. Basically, you're creating a myelin sheath with all these glial cells, and it'll be easier for you to, you're making structural changes to your brain through studying, which is kind of neat to think about. So that's it. I mean, they went into a little bit more detail about sodium channels, about potassium channels, depolarization. I'm not going to worry about that. I'm going to worry about axons, dendrites, action potentials. We're going to stay on that level. So I just want a general understanding. So we will be referring often to the neuron in some. I think I was supposed to, instead of being dumb and dumber there, I think I was supposed to say 2 ways. Anyway, in 2 ways, the presynaptic and postsynaptic, as well as discuss functions of the axon and dendrite. So an axon is always presynaptic, and a dendrite is always postsynaptic. Okay, so let's talk about the synapse a little bit. Kelsey, could I have you read the synapse, please?
The way the nerve cells communicate at the synapse is the very heart of the psychopharmacological. Did I say that right?
Yes, you got it.
Interest. This is because drugs affect these synapses. In fact, the neurotransmission is mediated by a group of chemicals the cells manufacture, which are known as neurotransmitters. There are at least 50 well-known neurotransmitters, but there are likely a large number of other ones yet unknown.
Okay, so thank you. Yeah, the synapse is the gap, fancy word for gap. And how about Justin, take us through this synapse slide, please.
When the action potential reaches the ends of the axon, it causes the release of neurotransmitters into the synaptic cleft or gap between the 2 cells. These neurotransmitters are actually stored in vesicles which move to the edge of the cell when it depolarizes, and then they release their neurotransmitter. As a rule, each cell releases only its one type of neurotransmitter at all times.
Okay, so basically at each site you have one neurotransmitter, one chemical. So each site is sensitive just to that one chemical. Let's see here. Jessica, you want to take that one?
Sure.
Okay.
After a neurotransmitter is released into the synaptic gap, it travels to the receptor site. Afterwards, it is released back from the gap, where it may either metabolize or it may return to the presynaptic side to be placed back in the storage vesicle for later use. Again, protein molecules transport the neurotransmitter across the cell wall and into storage, reuptake. Drugs may alter reuptake by blocking uptake channels in a number of ways. Autoreceptors may also increase or reduce the amount of neurotransmitter being released.
Okay. Autoreceptors are important when we're talking about overdose on like heroin, but we're not going to get into that. That's more of a psychopharmacology topic. So I want us also to be kind of aware of neural development. I've got a quick video here on how we develop neurologically.
Underneath the newfangled cortex, the brainstem, the limbic system, and the basal ganglia date back to the mastodons, the dinosaurs, and the first amphibians. In humans, the old parts of the brain oversee emotion and help build memories. They control heart rate and breathing. They also form intimate connections with the new brain, the cortex. Though less than a quarter-inch thick, the cortex is the brain's crowning glory. Among its roles, the cortex is our reality check. It filters and orders the outside world for us and allows us to see, touch, hear, and speak. The cortex is also the human thinking cap. All our plans, thoughts, and ideas originate in this layer. The cortex is packed with nerve cells. About 2/3 of all our neurons operate here. A piece of cortex tissue, no larger than a pinhead, can house 30,000 of these cells. Each neuron has a job: to communicate with other neurons. The brain works by forming networks among these cells. The long, spiny branches of the networks create a neural forest of astounding intricacy. Neurons use these communication lines to talk to each other with electric and chemical signals. Here under microscope are two neurons linking up. Though it may look like they fuse together, neurons don't actually touch each other. A closer look reveals that a tiny gap called the synapse separates their branches. This is where a message passes from one neuron to the next. The message comes from here, small sacs that store chemical molecules. When stimulated, these sacs release their molecules which cross the cell membrane into the synaptic gap. An electric zap allows this to happen. Meantime, the receiving neuron has special welcome sites for the incoming molecules. These receptor sites bind with the molecules. When they do, special gates open up. The gates let in a flood of charged particles, sodium and potassium ions, which start up a new electrical signal in the receiving neuron. This simple chain of events, an electrical zap followed by chemical changes, followed by another electrical zap, is the basis of all brain activity. It's how neurons speak to each other. Here, then, is the key to the brain's complexity. There are 100 billion neurons in the brain. Each neuron, like a bit player in a grand production, processes its information, then hooks up with as many as 50,000 other neurons to send and receive messages. 100 billion neurons times 50,000 connections. It's this complexity that allows us to think imaginatively. On their own, neurons aren't very bright. But put 100 billion of them together in a small space and let them all start talking to each other, and you start to get brainstorms. The trillions of neural networks, like an improvisational orchestra, create new ideas and connect different thoughts in a whimsical and sometimes inspired fashion. It's this impromptu ability to produce new things in our brains that allows us to progress, that quite simply takes us from here to here.
So what struck people? What stood out with that particular video?
Pretty fascinating.
Yeah.
I mean, just like what's inside of us.
What's going on right here?
What's really going on?
Other thoughts?
I really like how it started with even back in primitive ages, how our brain has evolved from what it was. I mean, back then we just had the basis, like, fight or flight, appetite, the brainstem part, and now we've evolved to have the cerebral cortex. We have the higher functioning as we've needed to adapt. And then because of that advancement, then the neuronal advancement, I think it's really complex and interesting.
Yeah, thanks, Brittany. I like that it went into detail about because we kind of touched on those older brain structures, last class, the brainstem, the midbrain, amygdala, those things. It touched on those. I was amazed when I watched this the first time, and every time I think about it, that our cortex, I showed that big picture of cortex, and it's this big, massive yellow thing up here, and it's like the biggest part of our brain. And how thick did they say it was? A quarter inch thick. And they said that's where 2/3 of our neurons are, in that quarter-inch membrane. It's crazy. And that would represent, for following, the evolutionary psychology side of things, that would be the last bit of our brain to kind of, come online, which separates us from the chimpanzee, from the different, animals on the planet. And think about how plastic that is, how we can have these new thoughts, these new ideas, and how it changes. It's really amazing. Any other thoughts before we go on?
And don't they say there's a correlation, like, with how many folds and stuff you have in your brain, and like
that's good. Absolutely. Children that go through periods of we talked about this a little bit in human development. If they go through some problems in utero while they're developing, they do have fewer folds. Yeah, very good. Absolutely. Any other thoughts? Just I love this stuff. I think it.
I wonder if you unfolded those, because in a physiology class we learned one time, like, as far as our venous system, if you were to pull out, and it's kind of gross, but if you were to pull out the veins, we have such a long veins in our arms that it could wrap around the earth twice.
Really?
So I wonder if you unraveled the brain, how far it would go.
That's amazing.
Just curious.
Yeah, that's a good.
If we have enough veins to wrap around the earth twice.
That's crazy when you think about all those intricate places where blood goes and how long that is. Cram packed in our bodies. So yeah, that's a good thought. I don't know. I don't have an answer, but that is interesting.
So do the folds decrease as you get older, and I don't know.
Like
so you got dementia or something?
Yeah. So we do have some brain cell death as we age. We don't necessarily lose those folds. I think you'd have to see kind of a major restructuring, of the brain to lose, its physical shape. I know it can happen. I know if a person has a stroke and you see an atrophy and a completely wiping out, certain areas of the brain, because with a stroke, like Brittany alluded to, we have blood vessels that go that keep us alive, that keeps us oxygenated, and so a person can take an MRI and see parts of the brain that have died off, and in that case, yeah, you probably would have kind of a reshaping, but for the most part, unless you're talking about a serious brain disorder like maybe a severe dementia, maybe Alzheimer's, I think you can definitely detect that under an fMRI, but for the most part, I think structurally our brains. Now, there's certain parts that change, like I talked about the hippocampus and others that are more malleable, are more plastic. But for the most part, once we hit adulthood, which is about 25, the prefrontal cortex stops, this massive generation of cells about 25, maybe 30. About that time, we're pretty static. as far as the overall structure. But good question. Anything else? Okay, so let's talk about drugs now. That's why we're here. Talk about drugs and how to counsel people. So drugs can have the following effects. They can decrease the activity of enzymes that destroy a neurotransmitter. One of the things that happens if a neurotransmitter is too active, it's out there too long, our body sends out little things called enzymes, and they eat the neurotransmitter. So let's say it's out in that synaptic gap too long, they're like, that doesn't need to be there. Kind of a cleanup crew. After reuptake of a neurotransmitter, they can alter the reuptake of a neurotransmitter, kind of like an SSRI, which we'll talk about in just a second. There's things called second messengers they can affect. They can interfere with ion channels. Alcohol does a pretty good job of interfering with ion channels. Change the amount of neurotransmitter neuron releases. So, like our vision cells that are constantly being, releasing serotonin. If you had a really bright light, or if you took a drug, you could actually get a flood. Think about how hallucinogen like LSD or mushrooms, they're going to flood your serotonin synapse with too much serotonin. Drugs can block the receptors as well as the autoreceptors, so cells can't talk to each other. So drugs can alter our neurological processes in several different ways. So I want to kind of make sense of it all with the way that drugs, if we introduce a drug into our natural neurotransmission now. So I've kind of alluded to it in the last slide. So the next few slides are really going to get into looking at how drugs are altering our natural process. So we can see we have natural systems that correlate with different chemicals. We have an acetylcholine system here, which if you blow this slide up, it's a lot here in the brainstem. We have a dopamine system, which goes through the reward centers, goes to the frontal cortex, in here in some emotional centers. We have a norepinephrine system. That's a fancy word for adrenaline. So again, here in the brainstem, if we get a rush of adrenaline, our heart's starting to beat. We're starting to breathe a little bit shallower, more quickly. Our muscles are getting a burst of energy. So it's activating a lot of things out here in our sensory cortex. This is the, let's see here. So this is the serotonin system here, and you see it's very complex. I mean, you've got it going back here to the cerebellum, you've got it going back here to the occipital lobe. Serotonin there's a lot of things that serotonin is responsible for. So I've alluded to a few of the brain chemicals, and they have certain properties, certain chemical shapes. And the way that we need to think about these to understand for our purposes is they're like keys. They each have a little different shape. And so if I'm going to, for instance, if I were going to try to put my car key over there in the door, am I going to have any luck? Probably not. However, if I take my office key and put it in the door, I think I have a key to this door, and it's going to work since it's got the right shape. And so for chemicals to work at all the different places in our brain, they have to be the right shape. So, for instance, let's say that, for sake of argument, let's say that I have a ficus tree right here growing in front of the sign, and I take a couple of leaves off that ficus tree and I chew them up and I swallow them. What's going to happen to me? Got a lot of puzzled looks.
Yeah, I haven't heard of that tree. Ficus tree.
What's a ficus tree? Yeah. Let's say it's an elm tree. If I take a couple leaves off an elm tree, am I going to get much of an impact?
I don't think so.
No.
Probably not. Maybe sick to my stomach. Now let's say this is a marijuana plant. Let's say I drive into Colorado and I accidentally stumbled across a farm
Yeah.
You accidentally
They're just everywhere, right?
anyway, and so I ingested a cannabis, and I ingested a part of a cannabis plant. What's going to happen to me?
I just eating the
You can
leaves.
start feeling that.
Let's say I eat a potent part of the plant. What's going to happen to me?
You're gonna get high.
Class is going to get pretty interesting in probably about 20 minutes. You're probably not be able to follow me. I'm probably not be able to think of words to come up with to communicate. I might start giggling, just incessantly for no reason, no apparent reason.
Get the munchies.
I might get hungry. I might need to get it. Could somebody run and get me a candy bar? I'm getting pretty hungry.
Spring brownies next week.
So yeah, the reason why is that? Why would one plant make a difference and not the other?
It's the chemical.
The chemical properties, because they're not the right shape. The cannabis plant has a chemical in it that looks a lot like an endogenous chemical in our brain. We have cannabinoid receptors in our brain, and so it works. Now the elm tree or the ficus plant,
Or nicotine.
nicotine, absolutely. Nicotine works because we have receptors. Nicotine works on dopamine a little bit. We'll talk about that. So serotonin's an important one. Dopamine's an important one. Norepinephrine, fancy word for adrenaline. GABA, we'll talk about that in just a second. So serotonin. Christina, you helped me out with this earlier. Serotonin has a lot to do with mood, but it also has a lot to do with senses. So it does more than one thing. Dopamine has more than one role too. Dopamine has a lot to do with movement, but it also has a lot to do with our feelings of pleasure and euphoria. So when something good happens to us, we're like, yeah, that's dopamine. Norepinephrine, again, that's giving us energy. GABA, we have a natural stress relief chemical in our brains. And so pharmacology has discovered that, pharmaceutical industries have discovered that, and they've given us medications such as Valium, maybe back in the day Quaaludes, then Xanax these days. There's a bunch of benzodiazepines that work specifically with GABA. Alcohol also works on GABA receptors. So think about, if most people have drank, think about the feeling of relaxation. It's working on your GABA receptors. Aspartame is actually a brain chemical. Anybody know what aspartame is?
Sweetener.
It is sweetener. So if anybody has a diet soda, if anybody's drinking a diet pop right now, flip it around and see. Most likely that's got a flavoring called aspartame, and it's a sugar substitute. It's also a brain chemical.
Really?
Yes. So if we're trying to equate, now we're thinking about our substance abuse counseling, and we're thinking about drugs of choice that people are using. Serotonin works a lot with LSD and mushrooms, the hallucinogens. A lot work on serotonin. But we also have drugs like Prozac, Paxil, Wellbutrin, Zoloft that work with serotonin. We'll talk about those in just a second for comparison. Drugs that work on dopamine, coke, meth. I'd also go ahead and include like heroin and morphine. They do release some dopamine as well, feelings of pleasure. Now, where they differ, coke and meth also activate your norepinephrine channels quite a bit, giving you energy. Not so much on the heroin or morphine. GABA, I've already talked about. Valium and Xanax work a lot with Valium and Xanax, and aspartame is NutraSweet.
So you can get you can get addicted to diet.
I don't know whether it's an addiction. I mean,
you have withdrawals though.
I think you can have withdrawals. I hear folks complain of headaches quite a bit.
Well, I think that might be the caffeine.
Could be the caffeine component, but I also have folks that have drank diet soda. I'm not the diet soda expert. I just know that when I heard about this as an undergrad, I didn't really drink a lot of diet soda after that. Just because, yes, hey Whitney.
Sorry to interrupt.
No, go ahead.
So, like GABA is relaxation, stress
That's a good question. I've not studied aspartame extensively in the brain. So that if you guys wanted to take that on as a research project, or I would be fascinated to find out what aspartame's role. Because honestly, because we have so few chemicals, we have about 50, 55 chemicals that we're aware of, and we have like 500 trillion connections. Those chemicals have to do more than one thing. I mean, they have to, like serotonin, a lot of times have to do many, many things. Dopamine does more than just induce pleasure. It also, like for instance, Parkinson's disease, you've heard of L-Dopa. That's working with one type of dopamine that's helping us move. You know, if anybody's ever watched the movie with Robin Williams called Awakenings, it talks a lot about that particular substance. But good question. Good question. I'd be interested to know what its role is. I've focused a lot of my time on understanding like the chemicals that people abuse. And to come back to the addiction, I don't know. Let's table your question on whether aspartame's addictive. I do know if we're looking at all of these things, you know, you could kind of make an argument that, well, I could maybe get addicted to like a mood-altering chemical, but not necessarily. Where the addiction really happens is this chemical right here. This one is very clearly tied in the research and in all scopes of medicine and science. Dopamine is the addictive substance because we'll talk about it in just a minute. Okay, so first of all, before we get to dopamine, I want us to see how like a legal drug that you can get prescribed works in our brain. So let's take a look at the antidepressant class of medication. Let's see, I haven't heard from Mario. Mario, could you take us through these drugs that work on serotonin?
Sure. Prozac, Paxil, Zoloft, Wellbutrin, and Effexor.
Yes, sir. So, you've never heard of Effexor?
I've heard of the other one. But
Okay. There are a few more out there now since I've made this PowerPoint, but most antidepressants work on serotonin. You have some tricyclics that are a little bit older that work in a more complex way, but for our purposes here, trying to understand basic processes of how drugs alter your brain functioning, I'm gonna use this one. Let's see. Let's go up a little bit. So here's how they work. So normally, let's say that you guys put in a lot of effort for our midterm. You guys, or am I having 3 exams? Am I having 3 exams in this class? I think we're having 3. So let's say you put in a lot of work for the first exam, and you're studying the slides, you're studying all the notes that you've taken, and you take the test. Then you're on pins and needles, man. I really wanted an A in substance abuse counseling. I really wanted an A. And so I give you back your grade, and you're like, yes, I got an A. Okay. So at that moment, your brain fired right when you saw that A, and your serotonin.
Never mind, you're back.
What?
We lost it for a second.
Okay. All right, am I back on all channels?
Yeah.
Ponka, test. Is Ponka out there?
Yeah.
Is Alva out there?
Yep. Yes.
Okay, and I can see Woodward, so I'm going to take it. Kevin, we good?
Yep.
Okay, cool. All right, so right when you get that A, your serotonin channels open up, and you get some happy chemical release. So serotonin, where's my red marker? There it is. Not that it has to be red, but... Uh-oh. It sounded like I lost him again.
No, you're good.
Okay.
They're just froze.
Serotonin. So serotonin is released. And we experience happiness. Now, when people are depressed, things happen in their lives that affect our happiness. Lots of times when people become depressed, very bad events have happened. Let's say that Yesterday was the anniversary of my father passing away, so that's a horribly depressing event. Let's say that I wrecked my car. Let's say that my house got foreclosed on, and my wife left me with my 2 kids because I wasn't able to provide for them. Let's say that I know these things.
It's so sad.
I know it's horribly sad. It's horribly sad. It's
That's
like
a rough time.
that's a rough patch. But things happen to people that cause depression, and then we get chronic. What happens is in depression, one of these theories of depressions is that, okay, let's say that I'm going through school and I put in that time and somehow managed to get an A on that exam, on that first exam. Okay, great. Oh no, I hate it when it doesn't work. Okay, great. I got a little bit of serotonin. But what happens is the vacuum kicks on really quick and sucks it right back up. And so you get a little bit of satisfaction, but not much at all, because so many other things are weighing down on your life. And so what what Prozac and Paxil do is they come along and, okay, I got that A, and I had all those bad things happen, but they stop the vacuum. So basically they block it to where the chemical is blocked out here, and I'll use a little blue for the. So you've got more serotonin floating around than naturally you would. So it makes the serotonin work harder. It blocks it. The way that you think about this is if you go to your pharmaceutical, you go to your pharmacist. These drugs are known as SSRIs. Oh, not 3 S's. Okay. Sorry about that. Let me pan out a little bit anyway. There we go. So, and I had somewhere along the lines lost a few. Maybe it was that
Super select.
It was that cannabis plant I ingested a few minutes ago. So bear with me if class gets a little bit weird. Just kidding. So anyway, so serotonin tells you where it's working. So again, we're talking about drugs like Prozac as the first one. Serotonin.
Wait, so let's just.
Excuse me. Yes. Like I said, bear with me. Selective. So it's picking out places in your brain where serotonin is, but it's not taking all of them. So it's trying not to impact the serotonin that's with your vision or with your with your senses, with your hearing. It's trying to select certain serotonin that have to do with your mood. Now there are side effects to taking SSRIs. Again, they have some sexual side effects, some sleep side effects, some other things, anxiety. But what it does, it's a reuptake inhibitor, which is a fancy word for meaning it shuts off the vacuum. It inhibits reuptake. Selective serotonin reuptake inhibitor, the SSRIs. So its name describes its action, SSRI. So now, that's how a legal drug. Yes, Brittany.
So, okay, for people who do struggle with depression, you said all the stuff that's going on with them causes them to not have as much serotonin. Is that right? When they do get that little jolt of serotonin, it sucks it up really quick, right?
Yeah, I mean that's kind of the theory. I would say that serotonin levels deplete because of all the other things that are going on.
So is that something that was there from like birth or childhood that they were born with? I mean, why don't they have as much serotonin? Is that known?
I would say that there's probably a confluence of events. It could be genetic. Depression has a big genetic component to it. It could be a lot of environment. I do know there's a confluence of events that usually lead to depression. I mean, some people kind of have chronic anxiety that can lead to depression. There's a lot of different things. But what they found, And you know, the SSRIs aren't perfect, and that's one thing I want you guys to get from this class, is that there really aren't any perfect drugs out there. Our brain is so complex, we're not able to look at 500 trillion connections and go, oh, well, I have a drug that will work on these 13,000 connections that control this. I mean, there's always going to be a side effect because of how complex that we are. And so like I mentioned, some of the side effects with SSRIs. One of the side effects in SSRIs with youth is increased suicidal ideation, or increased capacity for actually attempting suicide. So there's been kind of a black label warning for SSRIs with teens.
Do anxiety drugs kind of work the same way?
Anxiety drugs are a little bit different, and there's a lot of different classes of anxiety drugs. They, for the most part, like if you're looking at a Xanax or a Valium or even an Ambien, they're working at GABA channels, and the more GABA that you have, typically the more relaxed a person is. The problem with those drugs is that when you impact the GABA channels, you start impacting a lot of things. You start impacting heart rhythm. You start impacting, sleep patterns, energy patterns. There's a lot of research out there that says any prescription to a benzo over 3 months is detrimental, and you need to get off. I strongly, I've seen the research, and it's pretty strong. I mean, you have a lot of cognitive deficits. You see some cognitive slippage where people once had this brain capacity, and now it's shrinking because it's not allowing your brain to work. It's not allowing your brain to fire. Think about an alcohol. Somebody that's drinking a lot of alcohol, their brain's not functioning on all cylinders. Kind of the same way with these benzos. So they're not miracle drugs. There really aren't that many miracle drugs out there, especially when we're talking about psychology. But I know I probably didn't get the question, but I'll say it's okay. Those are, it's a little bit more complicated.
But those are for the high dose anti-anxiety drugs, the ones that really.
The anti-anxiety drugs, typically where they would be useful is somebody that's really experiencing panic, and these panic attacks. It does put a ceiling to a person's anxiety, and typically somebody that's got anxiety disorder, panic attacks, is debilitated. It will help that person that's debilitated function, but again, it should be used on a short-term basis, and I think that hopefully an episodal basis as well, not chronically. So now let's talk about dopamine. Dopamine does what? What is dopamine? Dopamine, it does quite a few things. It's effective in movement, but there's a dopamine, one particular kind of it that's released very sparingly and judiciously. So, for instance, did anybody have a snack in here while we were having class? What'd you have?
A fruit bar.
A fruit bar. Was it good?
Yeah, it was pretty good.
Good. I wish you'd have brought some for everybody. So next time you have to get the courier system like a day ahead of time. So, well, you're gonna have to send it Friday. So send us a bar. No, I like the energy bars. They're good. So what kind was it?
It's called That's It. It's an all natural.
All natural. All right. Good. So I had Cliff Bar earlier today. So yeah, it was pretty good. I had a little dopamine release. Remember your lunch. What did you have for lunch? Think about it. Hopefully it was a little satisfying. We get a little satisfaction from eating. We get some pleasure from eating. Think about your favorite meal. Think about maybe lobster tail dipped in garlic butter, and whatever, whether it's a ribeye steak or, we get more dopamine from something that we really like. We also get dopamine if, let's say that we entered the Powerball together and it's at 400 million, and we split it all ways with the class. We split it with all, 20 of us. We still get plenty, with 400 million. So what are you going to feel if you had $20 million extra in your bank?
Pretty good.
So we can imagine that, and just the process of imagining that, oh my gosh, I can do whatever I want. Just the process of imagining that, releasing some dopamine in our brains. So when we make lots of money, we get, so you think about going to the casino and somebody's putting in nickel slots and boom, they hit something, bing, yeah. You also get lots of dopamine when you have sex. So I talked about the male orgasm earlier today, and that's the most dopamine that a male can get naturally. Sorry, I was getting some feedback, so that's why I'm getting staccato in my speech. But that's the most that you can get. So think about your best sexual experience, and that's the most dopamine you can get naturally. So I want to pose a question. What do those three things, making money, eating, and having sex, what do those three things have in common with each other?
You need all three to survive.
Boom! Yeah, somebody's on there. You absolutely need all three to survive. Why? What happens if we don't eat? Starve. We starve. What happens if we don't make money in this society? We starve. We starve. We don't have a house. We don't have a job. We don't have anything. What happens if no human ever has sex again? Nobody, there's no more humans running around. These things are directly tied. Dopamine is directly tied to our survival. It is our feel-good chemical for a reason. It has helped us. Brittany talked about evolutionarily, the dopamine reward system has helped us figure out what's good for us and what's bad for us. The bad thing is, in today's society, we found a lot of things that feel really good, but aren't so good for us. So, the dopamine system, I have just a couple of minutes.
Our brains are complex webs of chemicals and nerves. Inside the brain, nerve cells called neurons are constantly communicating with each other to shape how we think, feel, and act. Let's have a closer look at these nerve cells. These are the ends of two neurons. The one on the right sends a message, the one on the left receives it. At first they look connected, but they're actually separated by a tiny space called the synapse. This is where messages are relayed. What we'll see next is how we normally experience pleasure. The sending neuron contains dopamine, the brain's pleasure chemical. When something good happens to us, this feel-good chemical is released into the synapse, where it connects with receptors. There, dopamine activates the receiving neuron, which in turn conveys the message onto the next neuron, creating a chain reaction that produces pleasure. After the message is sent, dopamine is recycled by transporters to be reused. This conversation repeats itself again and again, and gives us the feeling of pleasure and reward.
So again, it's pleasure and reward. It's been influential in our survival. It's been a good thing for us. So now we want to see what happens when we take drugs that work on dopamine. So we have these three things that fire dopamine: the quarter pounder with cheese, the big dollar sign, and sex. And I took away the sex picture just for politically correctness. Okay. Anyway, so when those things happen, boom, here comes some dopamine. Yeah, that's good. Those things are good. So same things happen if I had, let's say that I had a pile of cocaine or a pile of methamphetamine right here. Right. And so I had the pile of cocaine and the methamphetamine right here. And let's say that I ingested them somehow. Let's say for sake of argument, let's say that I smoked them, because all we have to do is inhale, and all the chemicals that are in lungs immediately go into our bloodstream. So let's say I smoked that, and immediately when that hits my lungs, every bit of dopamine in my brain fires at once. It's all out. So it's all out, floating in the synapse. Whew, the dopamine's out there. So your brain's like, wow, that's different. And it works like the SSRI in that it shuts the vacuum off. It's not getting sucked back out. So, wow, that's different. That seems rewarding. So, yes, we're feeling euphoria. We're feeling high. There's a problem with that, though. because your body's not used to, think about your best sexual experience is not going to last as long as cocaine or methamphetamine do in your brains. So what happens when the vacuum stops? What happens is we have enzymes that we mentioned that come along and start to eat. So let's say a person ingests cocaine, an effective dose lasts about 30 minutes. So enzymes start to come by and say, hey, that dopamine's not supposed to be out there. You're not supposed to feel this good for this long. And so they start to eat up your natural dopamine supplies. And so, a person will typically try to ingest more and ingest more and ingest more. With cocaine, eventually the enzymes wipe out the natural dopamine supply. And eventually people crash on cocaine. Methamphetamine's a little bit different. And this slide illustrates that. Methamphetamine looks so similar to your natural dopamine that it actually enters your brain cell. You see, cocaine kind of blocks, I'll take that away just a second. It blocks the reuptake, so it's bouncing around out here. Amphetamine just keeps on coming. So a person takes amphetamine, and the enzymes are like, okay, well, we gotta take that away. And a person keeps on doing meth, and person keeps on doing meth. And so now they're up for like 48 hours and 72 hours. And their body starts to freak out because the enzymes aren't doing the trick. And the person doesn't want to come down because, well, I'm feeling good. Your body really likes homeostasis, which is a fancy word for homo meaning same, stasis meaning state. Your body really likes the same state, which is like, think about the body of water. It's just got a few little waves on it, no big tsunamis or tidal waves. Your body likes balance. It likes things to be even keeled. And so it's like, okay, I'm up too far, I'm up too high, I need to figure something out. So what your body does, we'll come back to this, I'm running out of time. Sorry. So, sorry about the sign. So we'll come back to that. I'm running out of time. So what your body does, what happens to connections with meth? This is a receiving cell. And so these are the dendrites out here. This is your receiving cell, and it's getting all this information, all this dopamine is flooding this, and so it's it's sending on the dopamine this way, and it's like this nucleus makes a decision. It's like, I can't stand it anymore. I've got to have some peace. I've got to have some rest. The enzymes aren't doing the trick, so I'm going to do the trick. So what that nucleus decided to do right there was to cut it off and shut off the connection. So what did we say, 5,000 connections? Now we've got 2,500 pleasure connections on that cell. How well is that person going to feel then when they get off the meth? Are they going to feel good? They've impaired their ability to feel pleasure. This is the addictive process. What's that person going to automatically do because they don't feel right?
More.
They're going to try to find more. I just don't feel right without it. And so they do more. And so now they stay up and they keep doing meth for a few months. And they've wiped out their ability to feel pleasure. And they feel horrible. We'll get back to this. I'm running out of time today. One last thing that I want to... So they've done an experiment. They've done an experiment with rats. And they've given rats, they've been in a cage. And they've given them a choice of food, which, think about it, gives them a little bit of dopamine, and of cocaine and methamphetamine on another side of the page. What does the rat choose?
Cocaine.
Once the rat discovers the cocaine, it never goes back to the food. It is a death sentence if you give him a choice. Because its brain is so small, and it doesn't have a big cortex to think, oh, I'm getting skinny, I need to go get a cheeseburger. Oh, I might need to go eat some cheese, because its brain is lying to it. Its lower brain, which is where meth is active, and cocaine, starts lying to its cortex. This is way better than that cheese. Keep on doing that. And every rat becomes emaciated and dies because its brain is lying to it. The same process begins to work with adults. Parents may have started to, out with kids at the center of their life, work a close second, and they start to ingest drugs and alcohol. And all of a sudden, that takes preoccupation. That starts to move the kids and work to the side. and eventually takes over. This is what you're combating. This is what you're working against when you're working with people that are addicted, particularly to very addictive substances, like we mentioned with cocaine and methamphetamine. This is where we're going this semester. We're trying to help people that have, on some level, and there's a spectrum. Some people could be very addicted. Some people, there's a spectrum of addiction that we work through as well. So, like the low, moderate, and significant substance use disorder, that's how we scale this. This is how we understand this. And so this is how we're going to work through. This is how we're going to learn techniques by keeping this in mind that folks, their brains are lying to them. So what can we do? What are the techniques that we can use that are going to get through, that they're going to listen? So hopefully you got something from this class. This is where we're going this semester. Any last questions?
I looked up on Google about the aspartame, just out of curiosity.
Yes.
And it said they're still doing research, but they think it's because it affects the way that dopamine is absorbed. So they think that the quality may be in the fact that it affects the absorption of dopamine.
Really?
But they're still doing further research.
Nice work, class. Yeah. Very good. All right, well, I will see. Anybody have any questions over the break, please send me an email. Otherwise, I will see everybody on Monday.
We just want to let you know OPSU has been here. We think you forgot about us over here.
Oh, I did. Hey, I'm sorry, Cassie. I'm sorry. Okay, so you're both out there. You're both out there.
Yeah, Cassie and Ashley.